Hello everyone, this is Longhao Yang. Today I'm gonna talk about the 8.4.1 stack hunt example and its variation examples. And this slide is about the theorem we will use today. Both theorems are telling us that how to check the population state is evolutionarily stable or not. And today's example will illustrate the theorem 8.5, number 3, and I will put the theorems here just for you to review that. And so let's begin to start the real examples. For the stag hunt game, that the hunter has the choice to hunt either the stag or hare. So let's use the S for the stag and H for hare. So both the hunter 1 and hunter 2 has the choice of S or H. And if both of the hunters choose to hunt the stags, then both of them get the same payoff, which is 2-2. And if the hunter 1 chooses to hunt the stag and hunter 2 chooses to hunt the hare, then they got the payoff 0-1, which is the stag will run away and the hunter who hunt the hare will get the payoff. So the same as the HS strategy, the payoff is 1-0. And if both of them cooperate and hunt for the hare, then both of them get the less payoff, but both of them will get the same benefit, which is 1-1. And let's write in the theorem 8.5 way. Let's use the ABCD for the illustration. So the 2-2 is AA and 0-1 is BC and 1-0 is CB and 1-1 is DD. So under this case, we can see that is the third case of theorem 8.5, which is the A is greater to the C and D is greater to B, which is 2 greater than 1 and 1 greater than the 0. It's case number 3. So in this case, we will use the best response method to find the pure strategy Nash equilibrium. So let's do the process. Let's say if the hunter 2 choose stag, then the hunter 1 choose stag will get a higher payoff. And if the hunter 2 choose hare, then the hunter 1 will choose the hare for higher payoff, and the same for the hunter 2. So we will see that the Nash equilibrium for the pure strategy option is SS and HH. So we can write it down as pure strategy Nash equilibrium is RSS and HH. And both the pure strategy are symmetric. For symmetric, we get the definition is pi 1 SI equals pi 2 SI. And both of them are the strictly Nash equilibrium. So we can say that both of them are evolutionarily stable. And next thing we will need to check is for the mixed strategy Nash equilibrium. And in this case, let's say we use the equation for this theorem, and there is an assumption for the probability P is that P equals D minus B over A minus C plus D minus B. And we plug in this number, so it's 1 minus 0 over 2 minus 1 plus 1 minus 0, and the result is 1 over 2. So we can get the P is 1 over 2. Of course, 1 minus P is 1 over 2. And because both strategies are active, and we can find it by the fundamental theorem 5.2. Theorem 5.2, we can say that this one is also the mixed strategy Nash equilibrium. So after we check this, the next thing we will do is to check if this mixed strategy Nash equilibrium is evolutionarily stable or not. So let's check evolutionary stability of the mixed strategy Nash equilibrium. So by the theorem 8.1, we can say that for the criteria A, there is a typo. For the criteria A, the pi 1 sigma sigma needs to greater or equal to pi 1 tau sigma. And we know that the Nash equilibrium is mixed strategy Nash equilibrium, so it's naturally satisfy this criteria that pi 1 S1 sigma, of course, is greater or equal to pi 1 S2 sigma. And this criteria is satisfied, and then we can check the criteria B. It says if pi 1 sigma sigma equals pi 1 tau sigma, then we need to satisfy the criteria that pi 1 sigma tau is greater than the pi 1 tau tau. And for this one, we can check that if pi 1 sigma tau subtract pi 1 tau tau, check it what is negative or positive, so we can see which is bigger. And this equation equals to the minus p minus q squared multiplied by a minus c plus d minus b. It's an equation that showed in the book that we can check after the induction is the final form of the equation, so we can directly use it, and it's equal to negative p minus q squared. It's always positive for this part, and it multiplied by 2 minus 1 plus 1 minus 0. So the second part is also negative, so this part is negative and this part is negative. So for this result, it should be negative. So in the end, we can see that pi 1 sigma tau must smaller than pi 1 tau tau. So in this case, we can get the result, the mixed strategy Nash equilibrium, which is sigma sigma, is not evolutionary stable. That's the conclusion for the example 8.4.1. And then let's make some variation to this example. And for this one, the payoff will be slightly different. When the both hunter choose to hunt the stacks, they will get the same payoff as 2-2. But if they choose to hunt the different animals, like one of them hunt the stag and the other hunt the hare, then they will get the same payoff but smaller, which is 1-1. And also for the HS, and if both of them hunt the hare, they will get the same payoff, which is 1-1 as well. So in this case, we can see that A is still bigger than C, which is 2 bigger than 1. But in this case, D is equal to B, which equals to 1. And we use the best response strategy to find the Nash equilibrium. So when hunter 2 choose to hunt the stag, and hunter 1 will choose to hunt the stag as well. And if hunter 2 choose to hunt the hare, then hunter 1 choose stag or hare will make no difference. And same thing happens for the hunter 2. If the hunter 1 choose to hunt the stag, then hunter 2 will choose to hunt the stag as well. And if hunter 1 choose to hunt the hare, then it makes no difference for hunter 2 to make the selection. And after this process, we can see that the Nash equilibrium is the SS and HH for the pure strategy Nash equilibrium. But in this case, we can clearly see that the SS is strictly dominant strategy, like it's strictly dominant the hare strategy. Strictly dominant strategy. But the hare strategy is weakly dominant strategy. So let's say find out which is evolutionary stable. First of all, we can say that the SS strategy is strictly Nash equilibrium. And it's symmetric. So we can say that it's evolutionary stable. But for the and then we can check that if there is any mixed strategy Nash equilibrium, and we use the fundamental theorem, which will say pi I si sigma negative I equals pi I as pi 1 sh so we use that theorem, and so if we use the fundamental theorem, we can say that since both of the Hunter 2 is pure strategies, if we use the fundamental theorem, and according to that, since both the Hunter 2's pure strategy S and H are active, and each gives the same payoff to player 2 against to the player 1 against to the player 1's mixed strategy. So we can say that the pi 2 p multiply s plus 1 minus p multiply h for they choose s equals pi 2 ps plus 1 minus p h for they choose h. This payoff should be equal, and we plug in the numbers, then 2 multiply p plus 1 minus p multiply 1 equals 1 multiply p plus 1 minus p multiply 1. That should be equal, but it obviously is not equal. So we can say that there is no mixed strategy Nash equilibrium. And then one thing left that we need to check is the weakly dominant strategy HH. Is it evolutionary stable or not? So we will use this slide to figure that out. The HH is evolutionary stable or not. By this theorem 8.1, we can see that the first criteria is pi 1 sigma sigma greater or equal to pi 1 tau sigma. And we can say pi 1 sh equals pi 1 hh equals 1, which is satisfied. And for the left, the criteria B, if pi 1 tau sigma equals to pi 1 sigma sigma, then we need to check if the pi 1 sigma tau is greater than pi 1 tau tau or not. So in this case, pi 1 tau sigma equals to pi 1 sh equals to pi 1 hh equals to 1, but pi 1 sigma tau equals to pi 1 hs equals to 1, and pi 1 tau tau equals to pi 1 ss equals to 2. This 2 is not satisfy the criteria that the pi 1 tau tau is this one, and we will match the pi 1 sigma tau is this one, and obviously the pi 1 sigma tau is less than pi 1 tau tau. So the criteria number 2 is not satisfied. So the state HH is not evolutionary stable. So that's the whole process for when we determine the game and every state of the game is evolutionary stable or not. So that's all for today's example. Thanks for listening. Bye bye.